That kind of looks like a mess. I mean, really? Welcome to Lancaster Hi-Fi. I'm Stephen Lancaster. Let's talk about wiring an amplifier, or more specifically, rewiring an amplifier that was previously wired with printed circuit boards. I'm going to begin by reading an excerpt from Morgan Jones on layout of components. I'll just try to speak very eruditely because his writing is such. There are various approaches for positioning the smaller components, such as resistors and capacitors, ranging from one extreme to the other. 1. Position the components in a regimented manner in neat lines and use neatly harnessed wiring to make the complex interconnections. The parallel wires in the harness inevitably increase stray capacitances, but this method was used in the Quad 2 power amplifier. See figure 3.34. 2. Position the components in a regimented manner in neat lines, and either use hidden wiring, which can be untidy, leak, or exposed neat wiring, Mullard recommendations, to make the interconnections between components. This technique reduces capacitances compared to method 1, but can take up significant space. See figures 335 and 336. 3. Methods 1 and 2 had regimented rows of components enforced upon them by the layout of the tags on the boards. If that restriction is waived, then a small resistor no longer takes up the same amount of space as a large coupling capacitor, and space is saved. The hidden wiring becomes copper tracks, and the board becomes a printed circuit board, PCB. 4. The preceding methods are two-dimensional. Interconnecting wire length can be further reduced if the assembly becomes three-dimensional. Components are now soldered directly to valve sockets and, if necessary, to nearby standoffs or perhaps a tag strip. This is potentially the best construction method, but it needs careful thought to keep the components even reasonably tidy and accessible for testing/maintenance. Tag boards, tag strips, and standoffs are all useful ways of supporting components and joints insulated from earth. See figure 337. At valve impedances, practical inductances are completely insignificant except in the 0-volt busbar. So good layout in a valve amplifier requires low stray capacitances, and the best way of reducing capacitance between wires or components is to cross them at right angles. Capacitance to earth is minimized by short leads. One approach that is not immediately obvious is that sleeved wires have higher stray capacitance than self-supporting bare wires because epsilon sub r is greater than or equal to 1. It is the combination of these requirements that forces component layouts that appear to have been thrown together by an avant-garde sculptor. We thus arrive at the surprising conclusion that a good component layout probably looks untidy, but the converse is unlikely to be true. See figure 338. So bad component layout is also untidy, so tidiness not necessarily a good indicator of good component layout. And a good component layout probably does look untidy. And what I would hope is that I have used a good component layout in 3 dimensions, such as the 3rd dimension allows, because this chassis is pretty thin and doesn't allow for a lot of room in that 3rd dimension. But what I do try to do as I lay out these components is to cross things at right angles, to put as much space between leads as practical or practicable, and, keep things sort of tidy, but I will sacrifice tidiness for better sound, essentially. And I have had a case in which an amplifier that I built turned out to be pretty dang sensitive to the placement of components and leads. In this particular case, I was trying to test different values of coupling capacitor to see whether, to see what the effects might be. And so when I would put in the new replacement coupling capacitor, I would sort of scooch components out of their optimal configuration in order to get it there, and then I'd test in it, and it resulted in just horrible feedback and so on until I put it back into the optimal configuration, and at which point it was fine. And so good component layout can make a big difference, and bad component layout, as I believe Morgan Jones says in an earlier subsection here, bad component layout, bad wiring can ruin a good design. So it's a trick. Now, one thing I should maybe confess to reading Morgan Jones is that I should read more of this and more often. The fact that I gain inspiration and guidance for my wiring choices and component layout choices and so on should not necessarily imply that I follow his advice well or that I follow all of his other advice. As I was reading, sort of scanning through this chapter leading up to this passage, I was like, ooh, So I've still got things to learn, but I do want to also explain perhaps why this looks rather untidy and why I accept that untidiness or that appearance of untidiness. While it looks untidy, every wire and lead in there is placed intentionally. Now, whether I've always done the most optimal placement, probably not, because there are so many choices, so many potential wire routings and so on that, I'm not going to even try to pretend that it's, that this is the best possible wiring and layout. But that said, the wiring is intentional. I will go on to show you some wiring and explanations of said wiring in the footage that follows. Having got the power supply situated, next thing I will do is wire the tubes to the power supplies. I've actually kind of already done that for the output stage, except I will also wire it to the bias supply. This tube goes to this power supply, this tube for this power supply, and this tube for this power supply. And that will involve resistors from power supply to the plates. Then I think I will proceed with wiring up the cathodes of each tube. And finally, I will do the rest of the circuitry, the stuff in between the tubes, in particular, the coupling capacitors and the connections to the various circuits over here. And the reason I want to do that last is because that is the thing that is most subject to potential change later on. That is, do I want to stick with these values of these capacitors that are different from the original schematic? So, trials and tribulations and why I don't do both at the same time. Initially, when I was setting up the grid bias supply, I made a connection from here to here, and then put this resistor from here to here, which is the grid. Then when I was hooking up the screen grid supply, I thought, oh, I'd like to take the screen grid supply from here to pin 9 or here, but if I take it from here, then I have to cross this resistor, and that's silly. I should move it over to here. So I did that. So then I wired the screen grid supply from here to here, and I was going to set up a wire from here over to here. Then I was like, well, wait a minute, why would I do that? I'd have to run the supply over to here and then back over to here. Why don't I just keep it simple and run it from here straight to here, and then another wire from here to here. So I did that. But now I got this particular terminal wide open. Why? Just because it is. No reason now. I could move this back, but why bother? I've probably got enough terminals here to leave that one open. On with the show. So I've twisted all these wires. I was trying to braid them, could not get it right, but here we are. Now I need to run this one back to signal ground and this one to the feedback network, and I'm going to use this spare post right here. Back at it, folks. What do we have? Where are we? Still on the 1 amp. And the output stage pretty much fully wired up. The output stage wiring is pretty simple. And pretty much, I think, fully wired the input, or, you know, the AF amp stage and inverter or phase splitter stage, which is just this tube. And then on these preamp tubes, I've just hooked up the power supply and, of course, the heater. That is power supply here and resistor to plate, resistor to plate. Similarly here, power supply, resistor to plate. Oh yeah, down here. Resistor to plate, resistor to plate. Now the rest gets a bit more complicated because we got to tie in all these bits. So that'll be fun. Alright, here's something weird. The thing from pin 8, alright, that's the cathode of the phase splitter. That goes to the blue from the transformer. And pin 6 from the plate of the phase splitter goes to the brown. And I've got these oriented the way they were wired originally. That is, blue was this one, brown was this one. That crossed. Why? Why take the plate from here over to here and the cathode from here over to here? These are identically wired except for one is blue and one is brown, and the phase matters. if I want to do this in a way that makes sense to me so that they don't need to cross, all I got to do is switch blue and brown here. Okay, I gotta find places for all these monster capacitors. Going all orange drop film in the signal path. You know, the old one had a mixture of stuff in the signal path. Of course, it had these, you know, instead of these, and it had some other decent ones. But then some of the ones up here, for example, just your basic ceramic disc capacitors, which not super awesome for the signal path unless they're happen to be super awesome, but I don't know that they are. I mean, I don't know about these old ceramics, so, you know, never mind those. And nothing but the good stuff, but where am I going to put all this stuff? I'll figure it out. Yeah. I may be done, at least with the bottom. I will need to check up top to see if any components need to be replaced up top, but this is what I set out to do. Nice. So I'm doing the top of the chassis stuff now, replacing the resistors and a capacitor in this business here. And well, you can see easily on this one there's some more here, so I'll go ahead and replace all of these just to make it a clean sweep. In a lot of circuits, the precise value of the capacitor is not that important as long as it's in the ballpark. But for tone controls, the precise value is important. So I've gone through and chosen carefully. You know, these orange drops seem to be spot on value. The other ones, not so much, although, like, all the ones I had of these are 0.015 microfarads. Like every one I had was approximately 13 nanofarads or 0.013 microfarads. So I combined that with a 2.2 nanofarads, so then it comes out right on 15. This ceramic is pretty spot on. This one is good. I had to try a couple of those. I just remembered one more thing I want to do before I call the wiring done and proceed with testing. I twisted the ends of this wire to and from the switch over here, but I meant to twist these as well. And the reason is that this is AC, and this is now making a big loop, and it's right next to one of my ground wires from my input stage. So I'm going to disconnect these and twist them up. I may trim one of the, looks like this one is significantly longer than this one, so I may trim it in order to keep it all tight. So that brings me to the finish of wiring this amplifier. In the next part, I'll talk about and do some testing. I hope you've enjoyed and or learned something from this video, and if so, I hope you will subscribe to the channel, share the video, like the video, leave me a comment. If you have to tell me how crap a job I've done, then please do it politely. Anyway, I hope you'll tune in again, and if you do, I'll talk to you later. Cheers.
I fell into a